Assalamualaikum warahmatullahi wabarakatuh and good day. So in this video, we'll continue with example 9.17. We are still in the method of find the point estimation using maximum likelihood estimation. So in example 9.14, okay, you have found that the MLE of the binomial proportion P is given by P head equal with what over N. Okay, so this one binomial proportion, if you remember, you have mu equal to with NP. So P is Y over N lah. Okay, and then your variance, okay, actually NP Q. Okay, or NP 1 minus P. Okay, so the question asks you, what is the MLE for the variance of Y? So previous chapter, you know that your Vy will be NPQ, okay, or NP1 minus P, all right? So that one you must remember, okay? What is the mean and what is the variance of the common distribution that you have learned in this subject? So the variance of binomial random variable is given by this one, okay, as mentioned before. Now, this function, okay, this variance y function of the binomial parameter p, right? So therefore, we can do like this, okay, variance y equal with tp, okay, another function that we name, but here we have variance, in here we have parameter p. So tp equal with np1 minus phi. Okay, so it follows that the MLE of variance y is given by this one. That's means we want to find the variance y head. So this one is equivalent with TP head. And remember with P, we have P head y over N here. So that's why you can substitute the equation here NP1 minus P with this equation. Alright. So basically you have learned later this estimator, okay, this estimator is unbiased or biased. Okay, you will learn later in next video. But here, okay, we know that this is not unbiased, okay, which is mean biased. So however, using the result in exercise 9.65, okay, you can try look exercise 9.65. This one can be adjusted, okay, this one can be adjusted to make it unbiased. How is it? So look here. We have this one, okay, then we add with n over n minus 1, okay, and then this one, when you simplify, you will get n square n minus 1 times y over n times 1 minus y over n. So this one, you can check later, okay, in next video you will learn how to check this one biased or unbiased. Okay, basically from previous video, I've done a few example as well to check either this is biased or unbiased. So basically this one will give you unbiased minimum variance unbiased estimator. Okay, for TP equal with NP 1 minus P. Okay, so that example 9.17, you find this estimator, okay, using maximum likelihood estimation. Okay, so basically you have two method, okay, method of moment and method of maximum likelihood estimation. So make sure you know how to find the estimator using that method. So this is considered additional knowledge for you. Okay, some large sample properties of maximum likelihood estimator. All right, consider additional, but I just want to touch a few things here. So you can see that maximum likelihood estimator also have interesting large sample properties. That means if you have large sample properties, there are interesting thing to know. Okay, so suppose that t theta is a differentiable function of theta. That means this one can be differentiated. And then if you look in section 9.7, we have argued by the invariance property that if theta head is the MLE of theta, then the MLE of t theta is given by t head theta. This one what we have used in previous example. Okay, but you will learn this more detail later. Okay, so under some condition of regularity that hold for the distribution that we will consider, t theta is a consistent estimator for t theta. T theta head is a consistent estimator for t theta. So this one as well, you will, in previous video, you have learned as well a little bit how to check this estimator consistent for this one. Okay, so here we consider that t theta head is a consistent estimator for t theta. So in addition, if we have large sample size, the z will give you like this. So if you look before this, we have z equal to what? Z equal to x bar minus mu over sigma over square root n. Or maybe we have a y minus mu over sigma square root n, isn't it? So here you can see we have t theta head minus t theta divided by square root of differentiation of d theta with respect to theta square over n times expected of negative this one. Okay, this is the second differentiation of the ln function of the maximum likelihood. Okay, so this one has approximately a standard normal distribution. So in general, we want to say that if you have very large sample, the maximum likelihood estimator will also follow the same distribution as the population that you check. Okay, so in this expression, okay, you can see that the quantity function y given theta is the denominator, is the density function corresponding to the continuous distribution of interest. Okay, this one. Remember, we have find this one as a what? MLE, isn't it? MLE. You will find the likelihood function, and then you ln, and then you differentiate. So you can see that this theta, okay, using the sample, actually by using sample, we have sample. By using the sample, we want to see that this sample is follow the same population or not. Okay, so that's why here you can see that this consider the distribution of interest. That means if we are concerned about normal, so this is a normal distribution lah. If we are concerned about Poisson, this is a Poisson. Okay, evaluated at the random value of y. So in a discrete case, this analog result hold with a probability function evaluated at random value of y. So we will have p instead of f. Okay, because we have discrete. Okay, so substitute for density this one. Okay, it can be used as well for discrete binomial Poisson. Okay, but here if we have f, that means it's a continuous. Okay, so if we desire confident interval for this t theta, okay, we can use this z to have the formula. Okay, so you can see that one in section 8.6 lah. So basically we have this one. Okay, t head theta plus minus this one. Okay, so I will show the example. Okay, this is just application example. But here, important thing just to inform you that if we have very large sample size, and then we use the maximum likelihood estimator, okay, we will have this kind of thing as well. We will have Z as well, but this kind of equation. And then from this Z, we also can have the confidence in the interval like this. Okay, so in applied statistics, if you remember, you just use the formula. But here you can see that from this distribution, you will construct the central limit theorem or this Z. Okay, then from this Z, you will have this confidence interval formula. Okay, and remember in previous video, you have learned that we have a sampling distribution which related with normal distribution. So from that normal distribution, we can have what? Chi-square distribution, T distribution, and F distribution. So that's very important lah. That's a basic knowledge that you must have as a statistician as well. So we go through this example 9.18 very quick. Okay. Because this is I consider additional knowledge for you. Okay. So let's say we have a random variable with Bernoulli distribution. So you must so this is the Bernoulli distribution density function or mass function. Okay, because this is a discrete, so this is a mass function. So for y equal to 0 and 1. Okay, sebab Bernoulli you have 0, 1 only. So if y1, y2, yn denote a random sample of n from this distribution, so derive confidence interval for this one. Okay, and the variance associated with this distribution. So from example 9.14, you know that, okay, the MLE for the parameter p is given by this one. Okay, p head over equal w over n. Okay, instead of y, we use w. So to make it different, where w is what? Summation yi. I from 1 until n. Okay, so now it follows that the MLE for TP is equal with P1 minus P. Okay, because this one, remember, we have this kind of thing. Okay, then TP head will have like this. Okay, so in this case, in this one, in example 9.18, your TP will be this one. So you can have, you multiply, you get this one, then you differentiate with respect to P, you get 1 minus 2P. Alright, and then by using the, instead of the likelihood function, which is F, Y given theta tu, because this is a discrete, we use P here. So Y given P, so you have this density function, okay, or the mass function, and then you make it ln, okay, similar how to get the estimator tu. Okay, first you have this density function, okay, I mean the likelihood function, and then you make it ln, all right, and then you differentiate with respect for the first time, and then you differentiate for second time, and then you can have the expected value of this one. So when you have the expected value of this one, okay, you can have this y, which is this one, isn't it? This is second differentiation, the second order differentiation. So this one actually, you put it here. So you find the expected of this one. So you can see that when you have expected y, will give you this one, p. Okay, because it's a mean, isn't it? Y is p, so you just substitute, and then here is 1 minus p, and then you multiply, you simplify, you get this estimator. All right. So here the method is, the step is similar, except you have second differentiation, and then you need to find the expected. Okay. So this one, when we have n distribution. So actually here you can see that you have discrete variable, or you have discrete density function, which is Bernoulli, and then when you have n random sample of size, okay, this one you can approximately to normal actually. Okay, you can see from here lah, because we can have this central limit theorem too. Okay, all right. So this is the, okay, this is the estimator. Okay, and then we will find the confidence interval, which is they ask. Okay, so how to find it? You just substitute from the earlier formula. Okay, so you have this one TP head plus minus Z alpha over 2. You can see that when we have Z alpha over 2, is follow normal distribution. Okay, this Bernoulli. So here you just substitute what you get from previous slide. Okay, you just substitute the value, divide by this one. All right, and then finally you will have this equation. So this one is interval, confidence interval for P1 minus P, or PQ actually. All right, so that's why I said, if you know the ground, do you know from the beginning the fundamental of statistics, the theory of statistics ni, whatever data that you have learned in the future, and then it's different, it gives you different of variance, difference of mean, okay, you can construct your own formula, your own distribution function. Okay, so that's the groundwork that if you can see that, is very good lah. Okay, because in real world data, it's not follow common distribution sometimes. It follow a little bit, but sometimes the mean and the variance will be different. Maybe not PQ, it will be what? PQ minus 1, for example. Okay, but that's I want to share, or I want to show that sometimes if you, if you're good in ground of mathematics or statistics ni, in the future, if you have real world data, you can have it more accurate when you analyze. So I think that's all, okay, for this topic. So you can try the exercise, okay, page 4752. So usually the star one is quite difficult but important, okay. I hope you done or you do all the exercise. If you have problem, inform me, all right. Okay, so I think that's all for this video. Thank you, class.